Hi, and welcome to our presentation on our hovercraft design for ENGR 290. This is Team Drift. My name is Chris.
I'm Julian.
And I'm Ayman. First of all, we'll talk about the list of specifications. And for this particular project, we had a couple of requirements that we had to meet. First off, we had to design a hovercraft that completes a specific course distance of 1075 centimeters. Second, we had a time limit, so the course must be completed in 60 seconds. All of this within the Capellius environment, which has a flat ground, no water. We assume that the course will be the same one as mentioned in assignment 2. For the first specification was linear acceleration. And for that, the craft shall accelerate forward in straight segments. We have a total of 1,000 centimeters that will be traveled to complete the course in an acceleration of 0.32 centimeters per second squared with a precision of 0.01 centimeters per second squared. As for the verification, we will run the craft and measure the resulting distance over a set clock time. For the second specification, we base it off the same assumptions and the same requirements. For this one, we have angular acceleration. So the craft shall be able to turn in corners to avoid collision with the course. That in 75 centimeters is the distance that we had measured for turns. And in an angular acceleration, 0.34 radians per second squared. Also with a precision of 0.01 radians per second squared. In terms of verification, we will run the craft, measure the resulting distance over a set clock time, and then make sure everything is in order. Third on the list, we have the hover height. And for this specific specification, the craft shall hover at a height of no less than 4 millimeters, as we might encounter obstacles that reach a height of 3 millimeters. So 4 millimeters is just enough for the hovercraft to hover without any friction with the obstacles. And so with a precision of 0.1 millimeters, and for verification, we will measure the hover height that it's at least 4 millimeters over the ground. The next one on the list, we have the thrusters. And for this specification, the thrusters shall propel and steer the craft throughout the course. For that, we need a force of 0.03424 newtons and a torque of 0.003771 newton per meters. Those two with a precision of 0.001 newtons for the force and 0.0001 newton per meters for the torque. As for the verification, we will run the craft and make sure the thruster is being able to propel forward and able to turn when needed. Next one on the list, we have processing. And for this specification, the craft shall process data sent from the sensors and send them back to the thrusters. For this processor, we use the Arduino board Nano. It requires 32 kilobyte of flash storage and 2 kilobyte of RAM memory, that with a precision of 1 kilobyte. As for the verification, we'll make sure the processor is able to get and send data to multiple components of the hovercraft. And last but not least on the list, we have sensors. And for this specification, the sensors shall be able to sense obstacles and send data to the processor. The craft will need 3 sensors, 1 pointing forward, 2 pointing on the side at a 90-degree angle. The processing speed of these sensors is 6.66 hertz, and at an estimated sensing distance of 0.5 meters, and that with a precision of 0.01 meters. As for the verification, we'll run the craft to make sure the sensors sense obstacles and move the hovercraft accordingly. So for our decomposition diagram, we start with the power source that will be sending power to all 4 different components of the hovercraft. Starting with the sensors, they will be sensing information from the course environment, then sending data to the processor, which will then process that data and then send it back either to the directional axle motor or to the thrusters, depending on the situation.
For the autonomy approaches, we found we had basically 2 choices, whether to hug the left or the right wall, and we chose the left. The craft will essentially follow the left wall until no wall is present, in which case it turns left, or until a left and front wall are present, in which case it turns right. Next, we'll be looking at the top 4 designs considered, illustrated on screen. Mainly what differed between the top 4 designs were the placement of the thrusters. In the last design, we combined the best components of all 3 to make something very concise. Here are some more designs that we sketched, but they were considered to be too weak, so we discarded them before evaluating them in the matrix. Next, we'll be looking at the decision matrix, but before we go into that, we'll be talking about the criteria that we considered. First, we'll define the criteria. We have rotation, stability, energy efficiency, and simplicity. For rotation, it's the ability for the craft to turn upon its own center of mass. For stability, there are three components: balance, which is how the weight is distributed, control when it's turning, and its ability to regain control after turning. For the energy efficiency, it's how fast the craft is able to go compared to its own mass. So fewer thrusters will give better energy efficiency. For simplicity, it's how easy the craft is to design and how easy it will be to implement code. Next, we'll be looking at the decision matrix. And as discussed previously, we have 4 designs that we considered. Just to remind you, design 1 is on the left. For the first criteria, the first design offered maximum rotation, so it got top grades for that score. For stability, the balance was a bit lopsided, and it was difficult to regain control after turning, so it received a 1 out of 4. Energy efficiency and simplicity were both lacking as well, because there were too many thrusters. Next, we'll be looking at design 2, and just to remind you, design 2 is on the right. For design 2, it lacked the ability to determine itself, so it lost a lot of grades in rotation. Stability, the balance was lopsided, and the minimal thruster directions created a difficulty in regaining control after it turned. For energy efficiency, it was quite efficient, so it got 2 out of 3, and simplicity 2.5 out of 3 because it was easy to implement. Next, we'll be looking at design 3. Just to remind you, design 3 is on the left. For design 3, the thrusters were in both directions, allowed the craft to turn on itself very well, so it got top grades for rotation. It was slightly off balance, but mostly easy to regain control, so it got 3 out of 4 for stability, and it got decent grades for energy efficiency and simplicity because it was quite easy to implement and had few components. For design 4, we combined the best parts of our other designs. Just to remind you, it's on the right. For rotation, it had a strong ability to turn with a rotating thruster in the front. For stability, it was light and easy to maneuver because it had minimal components, and its thrusters covered each directional component. For energy efficiency, it was maximally efficient with few thrusters, and for simplicity, obviously with few components, makes it very simple to implement. As you can see, the totals are listed at the bottom. Design 1 got 7.5, Design 2 8.5, Design 3 11.5, and Design 4 had the highest grade of 13.5 out of 15. And it's for that reason that we chose Design 4.
Next, we'll be talking about the design sample calculations. I'll be going through step by step how we derived the values that were mentioned in our specification section. First, we'll talk about center of mass. As you can see, our components are listed there with their respective mass. We simply plugged it into the center of mass equation and obtained a 16.67 centimeters on the x-axis for center of mass. Since all the components are aligned on the y direction, as shown in the diagram to your left, we get a center of mass of 0 for the y-axis. Next, we'll cover the moment of inertia by using the formula I equals summation of mr squared. Again, the components are listed there with the respective radius compared to the center of mass. We plugged into the formula and obtained a 0.01109 kilograms per meter squared. Next, we'll be talking about the track. As shown on the bottom left, our track comprises of 4 segments of straightaway at 275 centimeters each, and 3 segments of turning at 50 centimeters each. In order to give ourselves the best opportunity to complete the course, we're going to give ourselves a buffer of 25 centimeters each for each section. This results in 250 centimeters for straightaway and 25 centimeters for turning. Adding it all up, we get a total track distance of 1,075 centimeters. Since the bare minimum we need is 60 seconds to complete the course, this gives us an average travel time of 17.92 centimeters per second, which 55.80 seconds is allocated for straightaway time. Since we have an allocated time of 55.8 seconds for straightaway, the time allocated for turns is 4.2 seconds, and using the following linear and angular acceleration equations, we could find a linear acceleration of 0.32 centimeters per second squared, and an angular acceleration of 0.34 radians per second squared. Now, in order to find the thrust needed to push the hovercraft, we need to find the total weight of the hovercraft. Adding up the total components again, including the body this time, we get a total mass of 1,070 grams. Now, using F equals ma, we have the acceleration and we have the mass. Times them together, we get 0.003424 newtons. Now, since we found the moment of inertia earlier with the angular acceleration, we can find the torque needed at 0.003771 newtons meters. And finally, here is a Gantt chart we provided earlier in the semester. As you can see by the diagram, we are currently at week 4 and evaluating our design. And next week, we'll be prototyping in Capella Sim. Thank you for listening.